For billions of years, the moon has orbited Earth as a constant presence in the night sky. It shapes tides, stabilizes Earth's rotation, and influences the rhythm of life on our planet. To the naked eye, the moon appears unchanged, following predictable motions through the sky. But modern measurements have revealed a surprising and scientifically significant truth. The moon is slowly drifting away from Earth. This process is extremely slow, almost invisible on human timescales, yet it represents one of the most important long-term changes occurring in the Earth-Moon system. The story begins with the origin of the moon itself. The most widely accepted scientific explanation, known as the giant impact hypothesis, proposes that the moon formed about 4.5 billion years ago when a Mars-sized object collided with the early Earth. The impact ejected vast amounts of molten rock and debris into orbit, and over time, this material coalesced to form the moon. When the moon first formed, it orbited much closer to Earth than it does today, possibly only 20 to 30,000 kilometers away, compared to the current average distance of about 384,000 kilometers. At such a close distance, the moon would have appeared enormous in the sky, and the tides produced by its gravity would have been far more extreme. Understanding why the moon is drifting away requires exploring the complex gravitational interaction between Earth and its satellite. The key factor driving the moon's outward movement is tidal friction. As the moon's gravity pulls on Earth, it causes the oceans to bulge, creating tides. But because Earth rotates faster than the moon orbits, these tidal bulges do not sit directly beneath the moon. Instead, they are pulled slightly ahead of the moon in its orbit. This offset creates a gravitational imbalance. The bulges exert a forward pull on the moon, giving it a small but continuous acceleration in its orbit. According to the laws of orbital mechanics, when an orbiting body gains energy, it moves into a higher orbit. As a result, the moon slowly drifts outward. The energy for this outward drift does not come from nowhere. It is taken from Earth's rotation. As the moon gains orbital energy, Earth loses rotational energy. This causes Earth rotation to gradually slow down, making our days slightly longer over time. Hundreds of millions of years ago, a day on Earth may have been only about 22 hours long. As the moon continues to move away, Earth's rotation will continue to slow down, adding milliseconds per century to the length of a day. Although imperceptible in daily life, these changes accumulate over geological timescales. The rate at which the moon is receding has been measured with remarkable precision, thanks to an experiment that began during the Apollo missions. Astronauts placed retroreflectors on the lunar surface, small arrays of mirrors designed to reflect laser beams sent from Earth. By timing how long it takes for a laser pulse to travel to the moon and back, scientists can measure the Earth-Moon distance with centimeter-level accuracy. These measurements show that the moon is receding at an average rate of about 3.8 centimeters per year, roughly the same rate at which human fingernails grow. This outward drift has been occurring for billions of years, but the exact rate has not always been constant. Geological evidence suggests that in the distant past, the moon moved away more slowly than it does today. The configuration of Earth's oceans, the positions of continents, and the depth of ocean basins all affect how tidal friction operates. For example, when the supercontinent Pangaea existed, tidal patterns were different, and the moon's rate of recession was not the same as the modern value. Earth's tidal behavior is closely linked to plate tectonics on Earth, meaning that the long-term evolution of the moon's orbit is influenced by plate tectonics on Earth. Understanding the moon's gradual recession also provides insight into the long-term evolution of Earth's orientation and stability. One of the moon's most important roles is stabilizing Earth's axial tilt, the angle at which our planet rotates relative to the plane of its orbit around the sun. Without the moon, Earth's tilt could vary wildly over time, leading to extreme changes in climate. The moon's gravitational influence acts to stabilize this tilt, keeping Earth's climate relatively predictable over tens of thousands of years. As the moon moves farther away, its stabilizing influence gradually weakens. However, computer simulations suggest that Earth's tilt will remain relatively stable for at least hundreds of millions of years. The increasing distance between Earth and the moon has consequences for the tides as well. Currently, the moon is the primary driver of tides on Earth, with the sun playing a secondary role. As the moon recedes, its gravitational influence weakens, resulting in progressively smaller tides. This change will not be noticeable within human history, but over millions of years, it will gradually reshape coastal ecosystems, sedimentation patterns, and the dynamics of ocean currents. Tidal forces have long been an important factor in marine life and coastal evolution, and the weakening of the tides will create long-term ecological shifts. Another important aspect of the moon's recession involves orbital resonance and the eventual future of the Earth-Moon system. The process will continue until Earth's rotation slows to the point where one Earth day matches the moon's orbital period. At that point, Earth and the moon will become tidally locked to each other, just as the moon is currently tidally locked to Earth. In such a configuration, Earth would permanently show the same face to the moon, and the tidal bulges would stop transferring energy into the moon's orbit. When this occurs, the outward drift will cease. However, achieving tidal lock would require an immense amount of time, likely tens of billions of years, far longer than the remaining life expectancy of the sun. The moon's drift also provides insight into past events in Earth's history. For example, scientists use ancient coral fossils and sediment layers to estimate the number of days in a year hundreds of millions of years ago. These fossils contain daily growth rings, similar to tree rings. By counting the rings in a year's worth of growth, researchers discovered that about 400 million years ago, Earth had roughly 400 days per year, implying that each day lasted around 21 hours. This finding aligns with the understanding that Earth rotation is slowing due to tidal friction, and supports the model that the moon has been gradually moving away for a very long time. Another line of evidence comes from the study of tidal rhythmites, sedimentary layers formed in tidal zones. These ancient structures preserve patterns that reflect tidal cycles and can be used to reconstruct the Earth-Moon system as it existed in the geological past. Analysis of rhythmites from hundreds of millions of years ago shows that tides were stronger and occurred more frequently, consistent with a closer moon exerting a stronger gravitational pull. Although the moon's recession is a natural and gradual process, it has implications for the far future of Earth. As the sun ages and evolves into a red giant billions of years from now, Earth and the moon will experience massive changes unrelated to their gravitational interaction. The sun's expansion will likely engulf the inner planets or at least drastically alter their orbits. Long before Earth and the moon reach a double tidal lock, the entire system will be reshaped by the sun's evolution. Thus, the moon's drift is part of a much broader cosmic timeline. Even today, the recession of the moon affects scientific fields ranging from geology to climate science. Precise measurements of the moon's distance are used to refine models of gravity, Earth's rotation, and the dynamics of planetary systems. The moon's behavior offers clues about how exoplanets and their moons may interact in distant star systems. Understanding the Earth-Moon relationship provides a framework for interpreting the formation and evolution of other planetary systems in the universe. The gradual movement of the moon away from Earth may seem like a small detail in the vastness of cosmic events, but it reflects the interconnected nature of gravity, energy, and motion within the solar system. The Earth-Moon system is not static, but dynamic, shaped by forces that act over billions of years. Tidal friction, rotational energy, and gravitational interaction create a slow but steady change that will continue into the far future. These processes are quiet, subtle, and invisible in human time, but monumental on geological and astronomical scales. The moon's drift is a reminder that even familiar objects in the sky are part of long evolving cosmic stories. What appears constant to us is in reality undergoing slow transformation driven by fundamental physical laws. The moon's movement away from Earth is a natural consequence of energy transfer and gravitational mechanics, an elegant demonstration of how celestial bodies continue to evolve long after their formation. What does the future hold for the Earth-Moon system? How will the continued weakening of tides and the slowing of Earth's rotation affect the planet over tens of millions of years? And what can this gradual drift teach us about the long-term stability of planetary systems across the universe? If you found this explanation valuable, make sure to like the video, share it with others who enjoy science, and subscribe to Wiseuse for more clear, in-depth explorations of our universe.